Okay, let's talk about uncertainty in angular momentum, specifically in a quantum mechanical system. So we are given a system that's in a particular angular momentum state. This state is described by the quantum numbers L equals 4 and Lz equals 4. And the question asks us what is the uncertainty in Lx for this state. We have a few options given h bar times the square root of 2 to h bar 0 or just h bar. Let's figure this out step by step. To find the uncertainty in any observable, let's call it A, we use a standard formula from quantum mechanics. The uncertainty delta A is equal to the square root of the expectation value of A squared minus the expectation value of A all squared. In our case, we want the uncertainty in Lx, so we need to calculate the expectation value of Lx and the expectation value of Lx squared for our given state. That's the state where L is 4 and Lz is 4. Right. Let's start with step 1, calculating the expectation value of Lx. A useful property here is that for any eigenstate of Lz, the expectation values of Lx and Ly are actually 0. But let's show this explicitly for our specific state. We know that Lx can be written in terms of the ladder operators, L plus and L minus. Lx is equal to 1/2 times the quantity L plus plus L minus. So the expectation value of Lx is the expectation value of 1/2 times the quantity L plus plus L minus in our state Lz. We can pull the 1/2 out. Remember how the raising operator L plus acts on a state Lz times Lz minus 1. And it changes the state to Lz minus 1. Minus Lz times Lz plus 1 and it changes the state to Lz plus 1. Similarly, the lowering operator L minus acting on Lz gives us Lz plus 1. Similarly, the lowering operator L minus acting on Lz gives us h squared of L times Lz. Now let's apply these operators to our specific state L equals 4, Lz equals 4. Applying L plus to the state 4, 4, we use the formula shown. Evaluating it, we find L plus times 4, 4 is 0. Next, applying L minus to 4, 4, the formula gives us h bar times the square root of 8 and it changes the state to 4, 3. Now, let's compute the expectation value of Lx for this state. We use the formula Lx equals 1/2 L plus plus L minus. This requires calculating the expectation value of L plus and L minus separately. For the L plus term, we have the inner product of 4, 4 with L plus acting on 4, 4. Since we found L plus acting on 4, 4 is 0, this entire term is 0. For the L minus term, we substitute the result we found, h bar times the square root of 8 times the state 4, 3. We pull the constants out of the inner product, leaving us with the inner product of 4, 4 and 4, 3. Since these states have different Lz values, they are orthogonal and their inner product is 0. Combining these results, the expectation value of Lx is 1/2 times 0 plus 0, which is 0. This is consistent with our expectation for an eigenstate of Lz. Okay, step 2, let's calculate the expectation value of Lx squared. We use the identity relating the total angular momentum squared operator to its components. This allows us to express Lx squared in terms of L squared, Ly squared and Lz squared. Taking the expectation value, we get the expectation value of Lx squared equals the expectation value of L squared minus the expectation value of Ly squared and Lz squared. For an eigenstate of L squared and Lz, we know the expectation values of L squared and Lz squared are given by standard formulas based on the quantum numbers L and Lz. For our specific state, where L equals 4 and Lz equals 4, the expectation value of L squared evaluates to 20 h bar squared, and the expectation value of Lz squared is 16 h bar squared. For any eigenstate of Lz, an important property is that the expectation value of Lx squared equals the expectation value of Ly squared. We'll use this. Starting from the identity for the expectation value of L squared, we rearrange it to express the sum of the expectation values of Lx squared and Ly squared. Now, using the property that the expectation values of Lx squared and Ly squared are equal, we can simplify this equation to 2 times the expectation value of Lx squared. Dividing by 2 gives us the expression for the expectation value of Lx squared. Finally, we plug in the values we previously calculated for the expectation values of L squared and Lz squared, substituting the values and performing the expectation value of Lx squared to be 2 times value of Lx squared. Okay, we're ready for step 3, calculating the uncertainty, delta Lx. We use our uncertainty formula, delta Lx is equal to the square root of the expectation value of Lx squared minus the expectation value of Lx all squared. From step 1, we found the expectation value of Lx is 0. From step 2, we found the expectation value of Lx squared is 2h bar squared. Let's substitute these values in delta Lx equals the square root of 2h bar squared minus 0 squared. 0 squared is just 0, so this is the square root of 2h bar squared. Taking the square root, we get h bar times the square root of 2. So the uncertainty in Lx for the state L equals 4, Lz equals 4 is h bar times the square root of 2. Looking back at our options, this corresponds to option number 1. The final answer is option number 1.